Welcome to the first chapter of our journey, where we define prompt engineering as the definitive bridge between human intent and machine probability. In this section, we will establish the foundational vocabulary and mental models required for advanced interaction with large language models. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to OpenAI, Anthropic, or any other AI research organization in any way. All trademarks belong to their respective owners. If you have spent any time experimenting with generative AI, you have likely noticed that the difference between a mediocre output and a masterpiece often comes down to the phrasing of your instruction. This course is designed to transition you from casual, conversational interaction toward a systematic, engineering-based approach to instruction design. We are not just typing requests. We are programming the latent space of these models to produce predictable, high-utility results. By mastering the frameworks we will discuss, you gain the ability to leverage these tools for data analysis, complex content creation, and workflow automation, regardless of your programming background. This is your opportunity to move beyond guessing and start designing. To understand why prompt engineering works, we must first accept that we are interacting with reasoning engines, not mere knowledge databases. Large language models like the GPT architectures or Claude operate by calculating the probability of the next token based on a massive, pre-trained statistical distribution. When you provide an input, you are effectively setting the initial conditions for a stochastic process, meaning the model selects words based on likelihoods rather than retrieving fixed facts. This is why a query about a specific historical event might occasionally result in a hallucination if the model prioritizes a high-probability path that deviates from ground truth. Recognizing that these systems are predictive engines rather than truth machines is the first step toward effective professional usage. A critical part of this interaction is understanding how the model perceives your input through the lens of tokenization and context windows. Every word, character, and punctuation mark you submit is broken down into tokens, which are numerical representations the model can process. These tokens consume space in a finite context window, creating a boundary that dictates how much information you can provide at once and how much the model can remember during a dialogue. When you exceed this capacity, the system begins to push older information out of its active focus, which can lead to a degradation in performance or memory. Designing your prompts requires a constant awareness of this technical limitation, ensuring that the most vital instructions remain at the forefront of the model's limited attention span. We also need to demystify the internal knobs that influence these responses, specifically parameters like temperature and top P. Temperature is a setting that determines the level of randomness in the output. A low temperature pushes the model toward the most statistically likely or deterministic responses. Conversely, increasing the temperature allows the model to select less probable tokens, which encourages creativity but sacrifices consistency in factual tasks. Top P works in a similar vein by limiting the pool of candidate tokens to a subset whose cumulative probability reaches a certain threshold. Understanding these controls allows you to toggle the model's behavior between a precise logical processor and an open, divergent creative partner. Finally, you must internalize that perfect prompting is an iterative feedback loop rather than a one-time event. Even the most carefully crafted instructions often require refinement through testing, evaluation, and subsequent adjustment based on the outputs provided. We will explore how to analyze model failures, identify the weaknesses in your logic, and optimize your patterns to achieve professional-grade results consistently. This is a practice of constant improvement where your ability to refine your instructions is just as important as your initial phrasing. We are now ready to begin this technical, rigorous approach to artificial intelligence interaction. I look forward to seeing you in our next session as we begin our study of logical frameworks. Welcome back. In this lecture, We begin our exploration of core logical frameworks by examining the specific mechanics of role prompting. When we interact with a large language model, we are essentially navigating a massive probability space where the output is determined by the statistical likelihood of the next token. By assigning a specific persona to the model, we perform a form of steering that restricts this probability space to a more relevant domain of discourse. Consider a request for medical advice. If we provide no context, the model may draw from a broad and potentially generic set of data, leading to a shallow response. However, when we explicitly instruct the model to act as a board-certified specialist in a specific field, we invoke a more focused set of weights associated with medical literature, technical terminology, and clinical diagnostic standards. This is not about the model possessing true expertise, but rather about aligning its internal predictive patterns with the vocabulary and problem-solving logic characterized by that professional role. The persona acts as a functional filter, conditioning the model to prefer specific linguistic structures and reasoning pathways that are typically absent in untrained conversational output. The heuristic of using the phrase act as is perhaps the most common entry point for role prompting. Its effectiveness depends entirely on the specificity of the provided definition. A weak persona, such as act as an expert, provides the model with very little guidance, as the definition of expertise is contextually ambiguous and fails to narrow the probability distribution meaningfully. A robust persona, conversely, defines the expertise, domain knowledge, and the desired tone with enough detail to anchor the response securely within your requirements. Instead of merely asking for an expert, you might define the role as a senior site reliability engineer with 10 years of experience in distributed systems, specifically tasked with diagnosing latency bottlenecks in high-throughput environments. This level of detail allows the model to prioritize concepts like observability, queuing theory, and load balancing, while simultaneously ignoring irrelevant, unrelated concepts that might have otherwise bled into the answer. One aspect that often goes overlooked is how role assignment influences the model's vocabulary and overall problem-solving approach in a nuanced, structural way. If we ask a general assistant to explain a complex software bug, it will likely provide a high-level summary suitable for a general audience. If we assign the role of a junior auditor looking for security vulnerabilities, the model shifts its attention toward input validation, permission models, and edge case testing, reflecting the mental model we have implicitly defined for it. This shift happens because the model is essentially conditioned on internal representation of these professional roles learned during its training. When we invoke the persona, we are effectively setting a mental model for the LLM that mandates a specific perspective, pushing it away from an average-based response and toward a more tailored, domain-accurate conclusion. This is the primary function of role prompting, to replace a vague request with a constrained, strategic framing that dictates how the model processes inputs and generates its final analysis. Maintaining this role throughout a conversation requires vigilance, as models naturally tend to drift back toward their baseline, conversational tendencies over long interactions. If you find that the model is losing its specific persona, you should consider reinserting the role definition or using periodic reminders to keep the interaction grounded. This is especially true in longer sessions where the context window begins to fill with extraneous conversational data, which might dilute the weight of your initial persona instructions. It is wise to periodically reiterate the intended perspective or to structure your prompts such that the system understands the role is a persistent constraint rather than a one-time instruction. By keeping the role prominent, you ensure that the model stays disciplined in its vocabulary and analytical framework, preventing the degradation of quality that can happen as the conversation evolves and moves away from the initial prompt setup. This consistency is what separates a trivial, superficial interaction from one that produces genuinely useful, specialized results. See you in the next lecture. Welcome back. In this chapter, we explore contextual grounding strategies, which are essential for bridging the gap between an AI's internal training and the specific requirements of your unique domain. When we interact with large language models, we are essentially communicating with a system that possesses a vast but static repository of general knowledge. The challenge arises when we require that system to operate within the constraints of private, proprietary, or highly technical information that was not present during its initial training phase. Contextual grounding is the practice of providing the model with a source of truth within the prompt itself, effectively defining the physical and abstract boundaries of the knowledge it is permitted to use. By supplying this relevant information, we significantly reduce the likelihood of the model hallucinating, which is simply the system filling gaps in its understanding with plausible sounding but objectively false information. This is not about trying to increase the model's overall intelligence, but rather about narrowing its focus to a specific set of verified data. When you force the model to look at the provided context before generating an output, you change the nature of the task from a general knowledge retrieval exercise into a synthesis and reasoning exercise. This distinction is critical for any professional workflow where accuracy is non-negotiable. To implement this effectively, we must manage the inputs with a high degree of precision, especially regarding how the model interprets the difference between instructions and external data. Without clear segmentation, the model might inadvertently treat a piece of source text as a new set of instructions, leading to what is known as prompt injection or instruction overriding. We prevent this by using explicit delimiters, such as triple quotes, triple backticks, or XML-style tags, to physically isolate the reference material for the operational directives. If you're instructing an AI to summarize a long document, you might place the content within document tags and then instruct the model to base its response strictly on the information contained inside those tags. By naming the container, you provide a semantic anchor that the model can reference during its processing phase. This structural separation is the first line of defense against cognitive drift, ensuring that the model understands the external data is a reference object rather than part of the prompt's logical command structure. Managing the context window is another layer of this strategy, as every model imposes a limit on how much data can be processed at once. While it is tempting to provide as much information as possible, overstuffing the prompt with secondary information often dilutes the model's ability to prioritize key facts and can lead to increased latency or decreased adherence to constraints. We must adopt a policy of filtering where we prune non-essential background material and prioritize mandatory knowledge that the model must integrate into the final output. If you are providing snippets for summarization, you should selectively extract only the segments that directly address the specific task at hand rather than dumping an entire folder of records. This strategy preserves space for more explicit instructions or few-shot examples, effectively increasing the density of relevant information within the available context window. Efficiency, in this context, is defined by the relevance-to-noise ratio, and you are the arbiter of that balance. When dealing with high-stakes professional outputs, such as legal summaries or medical analyses, the abstraction of boundaries becomes even more rigid. You cannot simply trust the model to know what information is sensitive or secondary unless you build explicit constraints into the grounding process. You must clearly state the negative constraints, such as explicitly forbidding the model from relying on external training data when answering questions about the provided source. This creates a closed loop where the provided context acts as the only acceptable input, effectively transforming the model into a specialized engine that operates exclusively within the parameters you have defined. By defining these boundaries, you minimize the surface area for errors and create a repeatable, auditable process for any technical task. The goal is to move beyond casual prompting and into the territory of deterministic output management, where every piece of information presented to the model has a distinct, defined function. I look forward to discussing how these boundary setting techniques translate into logical reasoning in the next session. Welcome to this session on chain of thought reasoning, a pivotal technique for enhancing the logical reliability of large language models. In this chapter, we will explore how forcing a model to externalize its internal monologue serves to bridge the gap between initial input and accurate output. When we interact with a large language model, there is a natural tendency to expect an immediate answer, yet complex problems rarely yield to a single pass of pattern matching. Chain of thought reasoning, or COT, shifts the paradigm by explicitly instructing the AI to articulate its reasoning process step by step before arriving at a final conclusion. You are essentially asking the model to show its work, which transforms the internal calculation tokens into a verifiable sequence of operations. This method is particularly transformative for tasks involving multi-step arithmetic, intricate project planning, or logic puzzles where the probability of surface-level error is high. Research has shown that when models decompose a problem into serial segments, they effectively navigate around the limitations of their own latent associations, as each preceding step provides additional context for the subsequent inference. By incorporating the phrase, "let's think step by step," or similar directive structures, we anchor the model's focus on the logical dependencies inherent in the problem. This is not merely a request for more words, but a mechanism to improve stability by creating an intermediate chain of thought that acts as a cognitive scaffold. To implement this effectively in a professional context, you must treat the prompt as a configuration of thought processes rather than a command for results. When you frame a complex business case, such as a strategic resource allocation problem, you're not asking for a number, but for an inference path. If you allow the model to skip the deliberation phase, it often defaults to the most probable token sequence, which may look grammatically correct but is logically hollow. By forcing a sequential decomposition, you ensure that every intermediate calculation token is generated in a context where the previous logic has already been stabilized in the model's history window. Think of this as forced state management. The model keeps a memory of its own logical path, preventing it from hallucinating a final figure that does not align with the premises. For instance, when planning a rollout, ask the model to first identify constraints, then evaluate dependencies, and finally propose a timeline based on both. This structured approach forces the model to synthesize information beyond its training data surface patterns, leveraging its internal weights to compute the best path forward. Stability in these outputs is highly dependent on how you define the boundaries of each reasoning step. If the reasoning process is too vague, the model might leap to convenient but incorrect conclusions because the intermediate constraints were not strictly defined. Effective prompting for latent reasoning requires that we provide the model with a clear logical structure or a template for how that reasoning should evolve. You should define the domains of the reasoning, such as separating the analysis of financial performance from the evaluation of competitor positioning. By isolating these domains, the model is compelled to process each as a distinct logical unit. If the model fails to reach a consistent conclusion, it is often because the step-by-step logic was not granular enough to catch a deviation in the internal tokens. Complexity, in this sense, is handled by partitioning it into manageable segments where the model can verify its own consistency before moving to the next logical phase. This does not just improve accuracy. It makes the model's decision-making process transparent and audit-ready for your stakeholders. Mastering this technique effectively eliminates the randomness inherent in single-token inference. While the time taken for the answer to generate will increase, the quality of the deduction makes this trade-off highly favorable in any environment where accuracy is paramount. You're transitioning from treating the model as a search engine to treating it as an analytical engine that can perform multi-step problem solving reliably. It requires discipline to write these prompts, as it forces the user to be as clear about the reasoning process as they expect the machine to be. Once you move past the desire for instant answers, you achieve a level of control that most users never reach. Practice designing these chains by thinking about how an expert human would solve the problem, and then encode that methodology into your directives. This is the foundation upon which all reliable automation with generative models is built. Take care to reflect on these logical structures before we continue. Welcome to this exploration of core logical frameworks, where we will examine the fundamental distinction between zero-shot and few-shot learning techniques. We will analyze how these strategies dictate the interaction between your intent and the model's pattern recognition capabilities. In the landscape of modern large language models, zero-shot prompting represents the baseline interaction where you provide an instruction without any supplementary examples of the desired output. This approach relies entirely on the model's pre-trained internal knowledge and its ability to generalize from your textual description of the task. While it is elegant in its simplicity, it is often brittle because you are asking the neural network to infer your exact requirements from potentially ambiguous natural language. When you ask a model to summarize a document without an example of a desired summary, you are essentially gambling on the model's alignment with your personal preference for tone and length. This is acceptable for common tasks like basic translation or general knowledge queries, but it frequently fails when the output requires a specific, non-standard structural format or a unique domain-specific cadence. The model perceives your instruction, maps it to a latent probability distribution of likely next tokens, and produces an output based on its broad training rather than your immediate local constraints. Few-shot learning, conversely, introduces in-context learning by providing a small number of input-output pairs within the prompt itself to demonstrate the required pattern. By including these examples, you shift the model's task from pure generation to pattern matching and completion, which dramatically improves consistency and accuracy. If you need a model to transform informal text into a specific log format, simply describing the desired output as structured logs is often insufficient to guarantee perfect alignment across every field. Providing 3 or 4 complete examples allows the model to observe the transformation, identify the underlying logic, and map your input to the anticipated output structure with much higher precision. The model treats these examples as a temporary context session, effectively focusing its attention on the parameters you have clearly demonstrated. This is not about training the weights in the traditional sense, but rather about priming the model's immediate inference state with the logic needed for the current iteration. Determining the optimal number of examples depends heavily on the complexity of the task and the current context window constraints of the model. In many scenarios, a single example, or one-shot prompting, provides enough information to clarify the intent sufficiently to resolve ambiguity. However, when the task involves complex conditional logic or highly stylistic constraints, providing a wider variety of examples helps the model navigate the edge cases of your requirements. You should aim to provide as many examples as necessary to cover the distinct types of inputs the model is likely to encounter during the task's execution. If the task is nuanced, more exemplars allow the model to learn the pattern and, crucially, ignore irrelevant variations in the input data. Overloading the prompt with dozens of examples can reach a point of diminishing returns or exhaust the model's attention. So you must find a balance where the pattern is clear, but the instructions remain concise. The actual formatting of your input-output pairs is as important as the quantity of examples provided to the system. To minimize confusion, you should use clear delimiters or consistent labels to separate your examples from the actual task you want the model to perform. For instance, labeling your demonstrations as Example 1 and Example 2, followed by a final input section, creates a clear structural hierarchy that tells the model exactly where the pattern ends and the new challenge begins. If you're aiming for a specific tone, ensure that your examples reflect that tone perfectly, as the model will unconsciously adopt the distribution of the features present in your few-shot set. Maintaining this consistency across long-running projects is often the difference between a system that produces fragile results and one that demonstrates reliable, professional coherence. By treating these examples as a strict guide, you lock in the desired behavior and prevent the model from drifting into unwanted linguistic territory. Ultimately, the choice between requesting a result via a zero-shot prompt and guiding the process through few-shot examples should be driven by the inherent complexity of the required output. If your output needs to conform to a strict schema, an uncommon style, or a bespoke formatting convention, you should default to few-shot prompting to guarantee stability. Zero-shot is a powerful tool for rapid prototyping and general inquiries, but it lacks the explicit corrective force necessary for professional, high-stakes automation. Learning to recognize when a task has crossed the threshold from general knowledge to specialized logic is a key skill for any practitioner. As you integrate these techniques, you will find that providing well-structured examples essentially acts as a short-term architectural scaffold for your model. This systematic approach ensures that you provide the necessary guidance without overcomplicating the context or introducing noise that might lead to hallucination. See you in the next lecture. Welcome back. In this chapter, we explore task decomposition methods, focusing on how to break down complex objectives into distinct, manageable workflows to improve model performance and reliability. When we approach a complex task, our initial instinct is often to draft a single, exhaustive prompt that encompasses every requirement. Yet this frequently leads to cognitive overload for the language model. By adopting task decomposition, we intentionally slice large, amorphous workflows into smaller, discrete units of work that the model can process with higher fidelity. We can think of this in terms of horizontal and vertical slicing, borrowed from software engineering principles, where you either separate the task into sequential steps that build upon one another or isolate specific layers of functionality. Horizontal slicing involves splitting a process into chronological phases, such as research, drafting, and final revision, where each phase is autonomous but contributes to the final result. Vertical slicing, conversely, involves extracting a complete, functional feature from the larger project, such as asking the model to perform a focused extraction of specific data types before attempting a broader analysis. This approach directly mitigates the challenge of instruction adherence when the context window is crowded with secondary requirements. By narrowing the scope of what the model is asked to tackle at any given moment, we effectively increase the relative weight of the instructions provided for that specific subtask. Designing a modular prompt system requires us to treat each prompt as a functional unit, where the output of one iteration serves as the ground truth or the contextual input for the subsequent step. This architecture is particularly effective for long-form content generation, where asking a model to write a 20-page report in one go will almost certainly result in hallucinations or a degradation of stylistic consistency. Instead, we segment the project into chapters or individual sections, forcing the model to complete the structural architecture of the document before diving into the specific content generation for its components. Imagine delegating the outline creation to an initial prompt, utilizing the structured list as an intermediary file, and then feeding that JSON or Markdown list into a series of iterative calls to generate the body paragraphs. This ensures that the model maintains a clear understanding of the overarching objective while remaining focused on the granular requirements of the current segment. Such a workflow provides a mechanism for auditability, as you can verify the validity of the intermediary outputs before they propagate errors into the later stages of the chain. In scenarios involving complex data extraction or multi-persona interactions, task decomposition becomes even more critical for accuracy. If your task requires a model to act as both a technical auditor and a client-facing communicator, you're better off separating these roles into distinct execution windows rather than attempting to juggle them simultaneously. By designing a pipeline where the first prompt focuses exclusively on extracting raw data into a neutral format, you reduce the noise that persona-specific language might introduce into the extraction logic. Subsequent prompts can then ingest this parsed, clean data to apply the specific tone or perspective necessary for your final output. This separation of concerns is a fundamental pattern for improving precision because it eliminates the competition between instructions within the model's attention mechanism. When a model attempts to weigh both formatting extraction rules and sophisticated persona dynamics in a single prompt, the quality of both tasks often suffers. Isolating them allows each step to receive maximum model attention. We are essentially engineering a pipeline that mirrors the way a human expert might tackle a multifaceted contract analysis, finishing the data aggregation before attempting the synthesis. See you in the next lecture. Welcome back. In this chapter, we explore how to sharpen our prompt output by enforcing strict boundaries and exclusionary constraints to ensure your AI behaves exactly as intended. When we discuss precision constraint setting, we are moving beyond mere suggestions and into the realm of architectural directives. An LLM, by its design, is a probabilistic machine that seeks to minimize uncertainty by predicting the next token, which often leads it to drift into verbose, flowery, or irrelevant output. To mitigate this, we must shift our focus from asking the model to perform a task to defining the hard boundaries of what the model must avoid. This is not purely about what you write, but specifically about what you explicitly forbid the model from considering. By implementing exclusionary directives, we fundamentally prune the solution space that the model explores before it even begins generating text. If you fail to define these negative constraints, you are implicitly giving the model permission to prioritize its own internal training biases over your specific procedural requirements. One of the most effective strategies for constraint setting is the use of negative prompting, which acts as a filter for unwanted behaviors or content. You should clearly articulate directives like do not include, avoid, or exclude at the very beginning of your prompt, as language models tend to pay more attention to initial instructions. For example, if you are generating a summary, you might instruct the model to avoid introductory pleasantries, do not include executive summaries, and exclude any speculative commentary. This is significantly more reliable than simply asking the model to be concise, which remains a subjective and ill-defined term. By being explicit, you replace the need for the model to interpret your style preferences with a deterministic rule set that it must follow to avoid penalty. This creates a logical boundary that prevents the inclusion of industry-specific jargon or unwanted formatting, keeping the output professional and lean. Linguistic boundaries are equally important when you need to maintain a specific tone or register throughout a complex document. If you're producing content for a technical audience, you might explicitly instruct the model to exclude marketing speak, hyperbolic adjectives, or casual conversational fillers. By naming the specific behaviors that are prohibited, you create a negative space that the model is forced to navigate around. Think of this as establishing a grammatical firewall that discards high-entropy, low-value tokens that the model would otherwise gravitate toward for the sake of fluency. You must ensure these constraints are specific and verifiable by a machine reading process, rather than relying on abstract concepts that vary based on the model's current temperature settings. When you quantify these exclusions, you achieve a level of consistency that is otherwise impossible to maintain in open-ended generation tasks. Moving into technical formatting, precision constraint setting is the only way to ensure downstream compatibility without the overhead of manual post-processing code. When you require a specific JSON schema, for instance, you cannot simply ask for JSON. You must define the schema requirements and explicitly negate the inclusion of conversational wrappers, markdown preambles, or explanatory text. A common failure mode occurs when a model adds a "here is your JSON object" header, which causes downstream parsing errors. To prevent this, you should define a constraint stating, exclude all markdown formatting, introductory text, and closing summaries. Output only the raw JSON object adhering strictly to the provided schema. This forces the model to ignore its conversational training weights and act solely as a data serialization engine. By treating the AI as an interface layer rather than a chatbot, you leverage these precision constraints to integrate model outputs directly into your existing software pipelines. Finally, you must consider the relationship between word counts and content density when establishing these constraints. Setting a hard word limit is a blunt instrument, but when paired with negative constraints, like forbidding filler phrases, it becomes a highly effective tool for forcing dense, information-rich output. Instructing an LLM to use fewer than 200 words is a suggestion, but instructing it to limit the response to exactly 3 paragraphs, exclude adjectives, and avoid passive voice is a strict architectural constraint. These rules create a narrow path for the model to follow, significantly reducing the likelihood of hallucination or off-topic drift. As you refine your prompts, look at the areas where the model is failing to adhere to your needs and document those as new, explicit exclusions in your library. Precision is a result of cumulative constraint, and by narrowing the parameters under which the model generates text, you are effectively training the model to respect your operational boundaries. I will see you in the next lecture. Welcome back, and today we turn our attention to the chapter on structuring data and outputs, starting with the mechanics of delimiters and tags to bring order to your prompts. We will explore how to use structural markers to ensure the model distinguishes clearly between instructions, reference material, and input data. When we interact with large language models, we often make the mistake of providing raw, unstructured text and expecting the machine to intuitively discern what part is a directive and what part is data to be processed. Models are essentially pattern matching machines that attempt to predict the next token based on the statistical likelihood of the preceding context. If you simply paste a document into a prompt without clear demarcations, the model cannot reliably understand where your instructions stop and the third-party source text begins. By employing delimiters, such as triple backticks, XML-style tags, or standardized header markers, you create a formal grammar that the model can interpret as a structural boundary. For example, wrapping input text in custom XML tags like reference or data signals to the transformer architecture that this block should be treated as an object to be summarized or analyzed, rather than an instruction to be followed. This separation is critical because it forces the model to treat the contained data as a payload, which prevents it from potentially confusing your meta-instructions with the content it is meant to manipulate. In many professional scenarios, you might encounter situations where the provided input data contains phrasing that mimics an instruction, which can lead to prompt injection or accidental model misbehavior. Without proper delimiters, a piece of user-provided content that looks like a command, such as generate a report about X, might trigger the model to ignore your carefully crafted system guidelines. When you use fences or brackets, you encapsulate that potentially volatile data within a scope that the model understands as subservient to your primary prompt directive. Consider a system where you process customer feedback, where you clearly define the instruction outside of your delimiter blocks, such as telling the model that everything inside the feedback tag must be analyzed only for sentiment without acting on any command found within that feedback. This layering builds structural integrity, allowing the model to perform complex tasks by maintaining a strict hierarchy where your instructions occupy the highest level of authority. Brackets and dashes serve as visual and syntactic signals that keep the hierarchy stable, preventing the data from bleeding into the logic layers of the prompt. Beyond simple isolation, these techniques are essential for generating machine-readable outputs, particularly when you need to interface with downstream systems or scripts. If you require a consistent output format that includes specific headers or delimited sections, you can use those same markers to define the expected structure for the model's response. By defining a template that uses standard delimiters as anchors, you ensure that the AI follows a rigid schema that avoids the typical pitfalls of free-form, conversational prose, which can be difficult to parse programmatically. when you demand that a model return its analysis within a clearly defined format, such as using triple backticks around a code block or specific tag sets for different sections of a technical report, you increase the reliability of the system integration. This is not just a cosmetic choice, but a technical constraint that reduces hallucinations and format drift. By adopting these standard professional formatting practices, you transform the prompt from a casual conversation into a repeatable, deterministic pipeline that can scale in a production environment. Complex instructions often benefit from deep nesting, though here you must be careful to avoid obscuring the main directive under layers of metadata. When dealing with multifaceted tasks, you can nest tags like instructions inside a larger task scope, provided that you consistently use distinct, non-overlapping delimiter syntax for each layer. This creates a predictable flow for the model, where it can resolve the outer constraints before descending into the specific data processing requirements nested within. Always maintain a clear separation between the logic governing the task and the content of the task, using the delimiters as the physical walls of your logic. If you find the model getting confused, it is frequently because the transition between instructions and context is too diffuse, so sharpening those markers is your first line of defense. By strictly adhering to these structural conventions, you stabilize the model's attention span, allowing it to focus exactly where you want it to be. See you in the next lecture. Welcome back. Today we are focusing on the mechanics of structuring output as tables and lists to ensure your AI-generated data is both readable and machine parsable. When we ask a large language model to process information, the default tendency is to produce long, flowing prose which can be difficult to scan or analyze. By specifying a structured format, we shift the burden of organization from the reader to the machine, effectively turning raw text into a data asset. Markdown tables are the most common starting point because they offer a native, readable grid layout that most LLMs handle with high precision. To get a consistent result, you must explicitly define your column headers within the prompt itself. For instance, rather than asking for a list of company data, you should instruct the model to create a 4-column table with headers for company name, industry, headquarters location, and annual revenue. You should also specify the expected data type for each column, telling the model to treat the revenue figures as currency or to abbreviate the industry names. This prescriptive approach reduces hallucination and forces the model to verify its output against the constraints you have provided. If you require data for secondary processing, such as importing it into a spreadsheet or a database management system, CSV formatted text is often a superior choice over visual tables. CSV provides a machine-readable stream of data that excludes the decorative whitespace found in markdown grids. When requesting CSV, it is crucial to explicitly define the field separator, such as a comma or a semicolon, and to clarify whether the first line should contain the header row. Be aware that models occasionally fail to escape commas inside string values, so adding a constraint like quote encapsulation ensures your output remains valid. You might instruct the model to provide a list of project milestones where every entry follows a precise schema of date, task, and status, separated by pipes or commas. This level of syntactic rigor allows you to programmatically ingest the model's response without having to manually clean or parse the input afterward. Transitioning narrative text into a structured grid is a frequent requirement in technical writing and data synthesis tasks. Imagine receiving a disjointed memo filled with project updates and needing to extract the key metrics into a clear comparison matrix. You can achieve this by framing the prompt to act as an extraction engine that maps amorphous paragraphs into defined columns. During this process, you must define the scope of the headers early to prevent the model from adding extraneous or subjective information. If the narrative covers 5 different products, instruct the model to maintain 1 row per product and ensure that each column contains only the specific variable requested, such as current status or technical specifications. This pivot operation is highly reliable if you provide the model with a clear mental schema for how to categorize the chaotic input document. Hierarchical lists are sometimes more effective than tables when dealing with complex, multi-tiered relationships between data points. When you need to show nesting or organizational levels, simple bullet points fail to convey depth, so you must explicitly instruct the model to use a specific indentation or symbol scheme. Requesting a bulleted list with clear parent-child relationships helps the AI maintain semantic consistency across large volumes of information. You can specify a format where primary points are marked with dashes and subpoints utilize a different, nested bullet character or numerical index. This creates a readable structure that acts as a functional map of the data, which is especially useful when generating technical documentation or hierarchical summaries. Consistency here is the key. If you do not specify the depth of the nesting, the model may arbitrarily decide where to branch its logic. Best practices for professional report generation require that you move beyond basic formatting and into strict alignment strategies. One significant issue to monitor is the tendency for models to drift in their formatting style when the output becomes too long. You should prepend each block of the report with a summary of the expected structure to act as an anchor, especially for long-form documents. If the report requires a series of summary matrices, ask the model to ensure that every table maintains the same column alignment and font style uniformity. By framing your intent clearly, for example, by stating that all numeric entries should be right-aligned, you set a professional tone that persists throughout the output. Verification is also part of the process. Adding a concluding instruction to perform a self-check on the list counts or table row totals can catch simple arithmetic or parsing errors. I will see you in the next lecture. Welcome back. We are now diving into the mechanical heart of machine-to-machine communication by mastering advanced JSON and schema-based output formatting. When we interact with large language models for automated systems, the natural language fluff that characterizes a standard chat experience becomes a liability. We require programmatic predictability, where the model acts as a reliable serialization engine rather than a conversational partner. To achieve this, we shift our strategy from plain text instructions to strict schema enforcement that mirrors the rigidity of integrated external tools. By providing the model with explicit structural constraints, we eliminate the ambiguity that typically results in malformed data and failed parsing attempts by downstream applications. This approach treats the prompt not as a request for text, but as a formal contract between the model and your API endpoint. The most effective way to communicate these constraints is by embedding TypeScript-like interface definitions directly into our system instructions. By defining a schema, specifying keys, expected data types, and required fields, we provide the LLM with a template that restricts its generative pathing. For example, if you require a JSON response containing employee metadata, you should explicitly define the expected structure as an object containing a string for the name, a numeric integer for the age, and a Boolean for status. This method is superior to simple natural language requests because it forces the model to categorize information into specific buckets rather than weaving it into narrative prose. When you define the key pair associations explicitly, you remove the guesswork often responsible for hallucinated keys or inconsistent naming conventions. Structural integrity relies heavily on the use of precise formatting directives that leave no room for markdown decorations or introductory commentary. In your prompt, you must explicitly instruct the model to provide the raw JSON object and nothing else, effectively creating a clean stream for your parsers. A common pitfall occurs when models wrap the desired output in conversational filler like "here is the JSON you requested," which often breaks automated ingestion pipelines. By setting a strict constraint that mandates an immediate opening curly brace and prohibits extraneous text, You ensure the output is immediately readable by machines without secondary cleaning logic. This refinement is a form of defensive engineering, ensuring that your system remains robust against the unpredictable nature of non-deterministic model outputs. Handling complex structures, such as nested arrays and deeply recursive objects, requires a slightly more deliberate approach to your schema injection. When defining the structure, represent multi-value fields as lists within your TypeScript definitions to clarify the expected hierarchy to the model. I find that providing a single representative example of the nested structure within the prompt significantly improves compliance across various model iterations. This grounding technique allows the model to map the abstract schema to a concrete implementation, reducing errors when parsing complex administrative datasets. You should also explicitly define how the model should handle missing information, such as requiring a null value or an empty array rather than omitting a key entirely. This consistency is essential when your downstream workflows depend on a fixed schema definition that cannot evolve dynamically at runtime. Maintaining this programmatic focus allows for seamless integration into even the most complex professional administrative workflows. When you treat the LLM as a component governed by strict data types, you transform it from a generic tool into a reliable cog in your technical infrastructure. By suppressing the model tendency to be verbose and steering it towards strict validation, you reduce the need for manual oversight and error correction. This is the difference between a prompt that produces a pretty email draft and one that feeds an automated database entry system. You are essentially shifting the burden of structure from the receiving application's code to the prompt itself, effectively outsourcing the validation logic to the model's sophisticated pattern recognition capabilities. See you in the next lecture. Hello. Today, we move beyond ad hoc interactions to explore how we can standardize the output generated by large language models to meet professional reporting demands. In an organization, consistency is rarely a happy accident. It is the result of deliberate design and the application of rigid constraints. When we ask an AI to summarize a meeting or draft a long-form executive report, the default behavior of the model is often verbose, meandering, or inconsistent in its formatting. To solve this, we must shift our focus from asking the AI to write a report toward providing a robust, reusable template that acts as a structural blueprint. By defining precise tone, document structure, and length constraints within our system instructions or prompt templates, we effectively constrain the state space in which the model operates. This ensures that the generated output remains predictable regardless of whether the underlying raw data changes. A well-constructed template functions much like a domain-specific language, forcing the model to map raw inputs into standardized fields. When you establish these templates within a shared prompt library, you reduce the friction of recurring tasks and ensure that every document produced by the system adheres to established corporate standards for tone and hierarchy. This uniformity is essential for downstream processing and for the humans who rely on these documents for decision-making. One of the most effective structural patterns for high-level documentation is the inverted pyramid technique, which prioritizes essential information at the beginning of the text. When prompting an AI, you should explicitly instruct the model to lead with executive summaries, key findings, and high-impact conclusions before descending into supporting data or background context. This mimics professional journalistic standards and ensures that stakeholders gain the necessary insights, even if they stop reading after the first paragraph. To enforce this, you can configure your prompt to require an explicit summary section at the top, followed by a prioritized list of action items, and finally appending detailed analytics or transcripts as supporting appendices. By structuring your prompt to demand this specific order, you prevent the common AI tendency to place findings buried deep within the text. This is particularly useful when processing long meeting transcripts where identifying action items can be like searching for a needle in a haystack. You can further refine this by asking the model to classify information based on its temporal or strategic significance, ensuring the most urgent tasks appear at the top of the output. Extraction of insights from unstructured data requires that we provide the model with a clear schema for what constitutes an insight or an action item. Instead of asking the AI to list the findings, you must define the semantic triggers it should look for, such as phrases implying commitment, deadlines, or strategic changes. You can achieve this by instructing the model to output data in a designated format, such as a table or a specific markdown structure, which anchors the extracted information to a consistent presentation style. When working with brand voice, remember that consistency is maintained by providing the model with a set of explicit behavioral guidelines or a few-shot example that demonstrates the desired tone. If the corporate voice is formal and concise, an instruction set that prohibits common filler phrases or superlatives will significantly improve document professionalism. By creating a prompt library that houses these validated configurations, you ensure that the logic applied to a monthly project report can be easily recycled for a quarterly business review. This disciplined approach to documentation transforms the AI from a general-purpose chat interface into a specialized tool for generating business-grade collateral. See you in our next session. Hello, and welcome back to our workspace as we examine the mechanics of dynamic content variation. We will discuss how to systematically generate diverse outputs from a single prompt structure, which is essential for effective A/B testing and scalable communication. When we approach the challenge of content generation at scale, the goal is to maintain a consistent core message while varying the delivery to resonate with different audiences or platforms. Many practitioners make the mistake of rewriting prompts manually, which introduces inconsistency and wastes significant effort. Instead, we should view the prompt as a template or a function that accepts variable inputs to produce contextually different results. By defining specific variables within your prompt using placeholders, such as target audience, tone, or platform, you can keep the structural logic of your instructions intact while shifting the nuance of the output. This approach is particularly effective in marketing when you need to test multiple subject lines or add variations against one another. By isolating these variables, you ensure that the variations you observe in the final copy are the result of intentional, controlled modifications rather than arbitrary shifts in the model's behavior. To control the creative range of your content, you must look beyond the prompt text and understand the influence of model parameters, specifically temperature and top P settings. While the prompt provides the instructions and the variables, the temperature acts as a dial for randomness. A higher temperature promotes creative, unpredictable phrasing, while a lower temperature keeps outputs closer to the most probable, conservative path. For A/B testing, keeping your prompt structure constant while incrementally adjusting the temperature directive within your instructions can produce a spectrum of creative expressions that retain the same foundational intent. Additionally, you should employ specific adjective directives to steer the model's stylistic output without altering the logic of your prompt. For example, explicitly instructing the model to use authoritative versus conversational language allows you to harness diversity without losing the reliability of the source message. Preventing repetitive patterning is a common concern when generating large batches of content, as models often fall into stylistic ruts if they are not prompted for variation. One effective strategy is to leverage dynamic input injection to continuously refresh the context in which the model operates. By rotating the examples or the target platform data in your prompt, you force the model to reevaluate the tone and focus, effectively breaking the tendency to output generic, monotonous text. If you are generating social media posts, you might pass a list of current cultural trends or specific pain points as a variable in each cycle of prompt execution. This prevents the output from sounding like a template and ensures that even automated content maintains a human-like variability. It is essential to monitor these outputs for semantic alignment, ensuring that the core messaging persists even as the aesthetic or emotional delivery changes. A/B testing thrives on these subtle, controlled variations, but their utility extends far beyond simple preference testing in advertising. When you architect a prompt that treats content as a fluid object controlled by variables, you create a robust system for internal communications, automated reporting, and personalized client outreach. The rigor of this approach lies in the separation of the content intent from the content expression, a principle that is fundamental to writing stable and reproducible system prompts. By investing the time to design these structured prompts with replaceable segments, you reduce the surface area for failure when you decide to pivot your messaging strategy. You no longer need to conduct a massive overhaul of your prompt library. You simply modify the input data that is fed into your established, tested structures. This leads to a higher degree of confidence in the outputs and a more predictable workflow during your testing phases. See you in the next lecture. Welcome back. In this lecture, we are going to explore the mechanics and strategic benefits of automated prompt chaining to handle complex, multi-stage objectives. Automated prompt chaining is the architectural practice of treating individual prompts as nodes in a directed graph, where the output of one large language model interaction becomes the input for the next. Rather than attempting to solve high-complexity tasks within a single, monolithic prompt, we decompose the objective into discrete, manageable subtasks that can be executed sequentially. Imagine you're building an automated content pipeline for technical documentation or research reports. You might start with a research prompt task, move to a structural synthesis prompt, and finish with a refined editorial review. This approach mimics a modular software design where each component has a single, well-defined responsibility. As we transition from simple prompting to system building, we naturally move toward these non-coded workflows that provide far greater reliability than trying to force a model to do everything at once. When we isolate each step, we significantly reduce the cognitive load for the model, which often translates into higher quality outputs. The primary challenge in designing these chains is managing state and context as data moves through the sequence. Because each request to an API is typically stateless, the developer must act as the bridge, ensuring that the necessary context from the first prompt reaches the third or fourth prompt without losing coherence. For example, if your first prompt generates a bulleted list of research findings based on a specific user request, that list must be programmatically injected into the variable structure of the next prompt. You are essentially creating a pipeline where data integrity is the primary concern. In practice, this often means normalizing the output of each node before piping it into the next one. A common failure point is assuming that the model will always provide a perfectly formatted JSON result, which is why your design should include verification steps or even meta prompts to scrub and validate the information before it cascades further down the chain. Visualizing the workflow as a graph helps developers identify potential bottlenecks where the model might deviate from the intended logic. Think of your prompts not as static text, but as functions with clear inputs and expected schemas for their outputs. When mapping these, consider what happens when a step fails. Does the process crash? Or does it trigger a correction loop that attempts to reprocess the problematic data? Truly robust chaining involves building in safeguards, like constraints on word counts, structural requirements, or even sentiment targets, that persist throughout the entire trajectory of the workflow. You should also consider the latency trade-offs, as chaining multiple calls inherently increases the total response time for the end user. This is a deliberate choice. We are prioritizing accuracy and depth over single-step speed. By managing the context manually, we remove the model's need to hold the entire history in one go, which is quite liberating for long-form generation tasks. Transitioning between these steps without human intervention requires a high degree of precision in how we request output formats. You want each link in the chain to provide structured data, such as a clearly delimited list or a strictly formatted JSON object, which is then easier to parse and pass along. If your research prompt generates a rambling prose paragraph, the subsequent writing prompt will inevitably struggle to interpret it accurately. Instead, aim for intermediate outputs that are machine readable and provide a condensed, dense representation of the desired information. Think of this as defining the internal protocols between your prompt functions. Once you have defined these handoff standards, the system becomes significantly more predictable and, more importantly, easier to debug when the output deviates from your expectations. This is where we shift from being mere prompt writers to being system architects for generative AI. See you in the next lesson. Welcome back. In this chapter, we will explore the mechanics of refining AI outputs through iterative feedback loops to ensure your results align perfectly with your technical requirements. Treating an interaction with a large language model as a single, immutable transaction is a common mistake that limits the potential of your prompt engineering. Instead, we should view these sessions as conversational processes where the initial output serves as a baseline for further refinement rather than a final product. When the model provides a response that misses the mark, the most efficient approach is to employ conversational repair techniques that address specific errors without discarding the entire context. You might find that the model has drifted from your stylistic constraints or included extraneous information, which requires a targeted follow-up prompt rather than a complete restart. By explicitly stating what should be retained while highlighting the precise aspect that needs adjustment, you guide the model back toward the intended trajectory. This is analogous to adjusting parameters in a software function, where you're not rewriting the entire codebase, but merely tuning an argument to achieve the correct return value. Positive and negative reinforcement play a crucial role in steering the model effectively during a live chat session. When the AI produces a component that meets your quality standard, acknowledging it reinforces that pattern and encourages the model to maintain that specific structure in subsequent iterations. Conversely, when you encounter a failure, clear and concise negative feedback, coupled with the correct instruction, acts as a corrective directive that limits the search space for the model's next attempt. Avoid ambiguous commands like "make it better," as these provide no quantifiable signal for the model to interpret. Instead, use explicit instructions such as remove the introduction and focus exclusively on the technical implementation details. This iterative signaling builds a temporary, session-specific logic that allows you to narrow down the desired output through incremental refinement. By consistently applying these reinforcement signals, you effectively reduce the variance in the model's performance over the duration of the conversation. Developing a personal feedback shorthand can significantly accelerate your ability to adjust tone, information density, or output structure. You might establish a set of directives, such as tighten the prose, increase abstraction levels, or prioritize code over commentary that the model can interpret consistently across different sessions. Over time, you'll begin to observe common failure modes in your prompts, such as the model consistently losing track of JSON formatting or defaulting to an overly verbose writing style. Rather than accepting these as inherent limitations of the AI, you should document these occurrences and incorporate them as specific correction directives into your baseline prompt. This transformation of reactive feedback into proactive constraints effectively upgrades your initial prompt for future use, creating a library of refined patterns that evolve alongside your expertise. Each interaction effectively becomes a data point that informs a more robust and precise starting point for the next challenge you undertake. See you in the next lecture. Welcome back. Today we examine the nuances of system instruction tuning, a critical layer in maintaining persistent model behavior. In the landscape of large language models, we often focus on the immediate prompt provided by a user to elicit a specific result. However, when building robust applications, relying solely on user-provided input is akin to building a house on shifting sand. System instructions serve as the foundational bedrock that exists outside the volatile stream of user queries. While a user prompt represents an ephemeral intent, a system instruction is a persistent directive that governs the agent's personality, safety constraints, and operational boundaries. By separating these concerns, we ensure that the model remains within a defined scope regardless of the adversarial or ambiguous nature of individual requests. This architectural distinction is not merely academic. It is the difference between a loose text generator and a controlled, reliable digital assistant. When you configure the system role, you are essentially setting the environmental variables for the model's cognitive process. The most effective system instructions act as a constitution for the agent, defining its persona, scope of expertise, and mandatory safety protocols. For example, if you are designing a technical support bot for a financial institution, your system instruction should explicitly state that the model must not offer personal investment advice while maintaining a formal, objective tone. This directive remains active across the entire life cycle of the conversation, effectively tempering the model's desire to hallucinate or deviate into topics outside its mandate. Without this global directive, a user might bypass your safety layers simply by asking the model to assume a different, less constrained persona. By anchoring these rules in the system role, you create a hierarchy of priority that the model is trained to respect above user-level instructions. The primary challenge in tuning these instructions lies in balancing the rigidity of the rules against the model's natural instruction following flexibility. If your system directives are too verbose or overly convoluted, the model may suffer from instruction dilution, where it struggles to prioritize which constraints take precedence. Conversely, overly sparse instructions lead to inconsistent behavior under stress. The secret is to use precise, imperative language that defines not just what the model should do, but specifically what it must categorically avoid. You should treat these instructions as code. They are a set of functional overrides that guide the model through every token generation cycle. Well-crafted system instructions transform the model from an unpredictable tool into a predictable, consistent, and safe component of a larger system. Managing potential conflicts between user input and system directives requires a clear understanding of intent override. Occasionally, a user will attempt to prompt the model to ignore its initial instructions, often through techniques like role-playing or hypothetical scenarios. If your system instructions are weak, the model may prioritize the most recent user prompt over the foundational directives. To prevent this, you should define your system role using strong, binding language that establishes a clear hierarchy of rules. By framing your instructions as an inviolable operational framework, you signal to the model that these directives are the ground truth against which all other requests must be measured. This approach effectively immunizes your application against most common attempts to bypass safety filters or institutional constraints. Testing these instructions requires an iterative approach, much like debugging a software library. After establishing your base system prompt, you must subject the model to a variety of edge cases intended to test the boundaries of its persona and constraints. Does the model maintain its professional tone when a user becomes aggressive? Does it correctly refuse to answer questions about topics it is explicitly forbidden from discussing? If the model fails these tests, you do not adjust the user prompt. You refine the system instruction itself by clarifying the ambiguity that caused the failure. By systematically isolating the system layer from the user layer, you gain the ability to improve the intelligence and safety of your application without introducing technical debt into your core prompt pipeline. See you in the next session. Welcome back. In this segment, we turn our attention to the systematic analysis of model failures, learning to diagnose why a prompt produces suboptimal outcomes. When a model fails to deliver the expected result, our immediate instinct is often to blame the underlying architecture, yet the root cause is frequently far more mundane. Before assuming the model lacks the capacity to perform a task, we must distinguish between inherent model limitations and the artifacts of poor prompt shorthand. We often provide instructions that are far too brief or rely on implicit assumptions that the large language model cannot reasonably infer. By mapping the failure points against a rigorous diagnostic framework, we can isolate whether the error stems from imprecise language, missing constraints, or a genuine gap in the model's training data. This approach allows us to pivot from frustrated guessing to structured experimentation. A persistent issue in long-form generation is context window drift, where the model essentially loses the thread of the initial instructions as the conversation or document grows in length. This phenomenon occurs when the weight of recent, potentially irrelevant tokens obscures the core system prompt that defined the original task. To mitigate this, we should employ techniques that periodically restate critical constraints or reinforce the primary objective within the prompt architecture. If you find the model beginning to digress, isolating variables is the most effective debugging method you have at your disposal. By stripping away large sections of a prompt and testing the model's performance on smaller, distinct components, we can identify exactly where the logic begins to unravel. Vague directives and ambiguous language act as force multipliers for failure, often introducing entropy that the model tries to resolve by guessing our intentions. Adjectives like professional, creative, or fast are fundamentally subjective, and relying on them invites the model to apply its own statistical interpretation of those terms rather than your specific style guidelines. We must replace such shorthand with explicit definitions, concrete examples, or specific output patterns that leave little room for subjective deviation. If a prompt remains unsuccessful, we should scrutinize the adjectives we have chosen and replace them with precise, observable requirements that the model can verify against the input data. This shift from qualitative to quantitative instructions is the hallmark of a resilient prompt design. Hallucinations often occur when a model is pushed to generate information beyond its reliable knowledge base. But we can drastically reduce this by enforcing strict citations and grounding. The goal is to bind the model's reasoning to a verifiable set of data provided directly within the prompt itself, effectively turning it into a reasoning engine rather than a knowledge retrieval system. By forcing the model to cite the exact portions of the provided text that support its conclusions, we expose the underlying logic for manual inspection. If the model cannot ground its response in the data we have supplied, it should be explicitly instructed to admit uncertainty rather than fabricate content. Placing these constraints on the output structure ensures that we maintain a clear audit trail for every piece of information generated. Understanding these failure modes empowers you to build far more robust automated systems. I will see you in the next lecture. Welcome back. In this lecture, we're going to explore the discipline of universal pattern optimization to ensure your prompts remain effective regardless of the underlying model. When we interact with large language models, we often encounter a deceptive sense of familiarity. We write a prompt, receive a reasonably coherent answer from GPT-4, and assume that the same prompt will function identically when ported to Claude 3.5 or Gemini 1.5 Pro. This assumption, while understandable, typically leads to degradation in performance. While these models share a common lineage in transformer architecture, their training objectives, alignment procedures, and tokenizer behaviors differ significantly. To achieve true portability, we must move away from idiosyncratic prompt construction toward identifying reusable blocks that leverage the common denominator of intelligence across these systems. By isolating the functional requirements of your task from the stylistic preferences of a specific model, you create a robust abstraction layer that minimizes the need for per-model reconfiguration. Portability begins with an inventory of your prompt structure. Most prompts contain static instructions, variable inputs, and formatting constraints. To optimize for a universal pattern, you should begin by decoupling the task definition from the persona or tone instructions, as these are often where models exhibit their most distinct biases. For example, a model trained heavily on RLHF for conversational agents might interpret a broad instruction as an invitation to be overly verbose, whereas a more raw model might require explicit steering to be helpful. By modularizing these into atomic building blocks, such as a preamble for setting constraints, a core instruction block for logic, and a schema-based exit condition for output formatting, you can standardize your inputs. When you encounter a failure on a specific model, you then have a clear target for adjustment rather than having to rewrite the entire prompt from scratch. One of the most persistent challenges in cross-model prompting involves the interpretation of structural cues like delimiters and markup tags. While most modern models have been trained to respect XML-style tags, the degree of adherence varies based on the underlying context window size and the specific training mixture. Using delimiters such as triple backticks or custom tags for context separation is a universal practice, but you must establish their meaning consistently across your own library of templates. If you decide that all external data references should be wrapped in semantic tags like data or context, apply this convention rigidly. This consistency reduces the cognitive load on the attention mechanism of the model, regardless of whether it is an encoder-decoder or a decoder-only architecture. It is essentially about creating a recognizable syntax that acts as a signal-to-noise filter for the model's processing layer. Model-specific keywords frequently trip up developers who seek a silver bullet prompt. Some models are highly reactive to terms like step-by-step or think logically, while others may interpret such instructions as a mandate for long-windedness that interferes with the core task. I recommend maintaining a library of fundamental constraints, the universal rules that you expect all models to adhere to, and then wrapping those in a thin layer of model-specific phrasing. Think of this as the difference between a high-level API and the implementation details for specific drivers. By standardizing your constraints for output, such as requesting JSON or specific summary lengths, you reduce the surface area for failure. If a model consistently ignores a constraint, move that constraint into a specialized section of the prompt that utilizes the specific keywords known to influence that model family's attention distribution. Finally, address the issue of update cycles and model drifting. As vendors update their models, even prompts that previously produced optimal results may suddenly begin to drift in quality. By maintaining a modular, file-based repository of your prompt components, you insulate yourself from these shifts. Instead of trying to patch a single monolithic prompt when results degrade, you analyze which block of the pattern caused the deviation. You then perform a targeted swap, perhaps by refining the system instructions to better align with a new model's update, without breaking the underlying logic of your data processing task. This approach transforms prompt engineering from an exercise in guesswork into a structured engineering process. It relies on the observation that the core logic of a problem remains constant, even when the interface for expressing that logic needs to be tuned for a new generation of language model. See you in the next lesson. Welcome back. Today we're going to explore how we can manipulate the probabilistic nature of large language models through temperature and top P settings. We will examine how these parameters fundamentally shift the physics of word prediction to serve different operational requirements. To understand temperature and top P, we must first accept that language models are essentially sophisticated probability engines. When a model predicts the next token in a sequence, it does not simply choose the most likely word. It calculates a probability distribution across its entire vocabulary. The temperature parameter acts as a scalar for these probabilities, effectively flattening or sharpening the distribution. A low temperature setting acts as a constraint, forcing the model to favor tokens with the highest probability, which leads to more deterministic and repeatable outputs. Conversely, Increasing the temperature distributes the probability weight more broadly, allowing the model to select tokens that are less likely, which introduces entropy and variation. This is the difference between a system performing a precise calculation and one engaged in imaginative exploration. If you're building a system for code generation or data extraction, this predictability is your primary requirement. In those scenarios, you want the model to behave like a calculator that returns the same result every time given the same input. By lowering the temperature toward zero, you suppress the model's tendency to wander off the path of statistical likelihood. Top-piece sampling, often referred to as nucleus sampling, provides a different mechanical approach to controlling the search space. Instead of adjusting the entire probability distribution, Top-P restricts the model to a subset of tokens whose cumulative probability exceeds a specific threshold. If you set Top-P to 0.9, the model only considers the smallest set of top-ranked tokens that collectively account for 90% of the probability mass. This naturally truncates the long tail of low-probability words, which effectively prevents the model from choosing nonsensical tokens that might appear if the temperature were high but unconstrained. It is a refinement technique that allows you to maintain a level of creativity while setting a hard boundary on quality. When you combine temperature and Top-P, you can fine-tune the model behavior with significant precision. For brainstorming sessions or narrative development, you might set the temperature higher while keeping the Top-P value restricted to ensure the model stays within the realm of coherent, albeit diverse, possibilities. This synergy allows you to mimic different degrees of focus versus spontaneity without needing to retrain or fine-tune the underlying weight models. Developing an intuition for these parameters requires you to evaluate the cost of error in your specific use case. For administrative tasks or technical documentation, the goal is always to reduce the search space to the absolute minimum, which demands a temperature of 0 and a low Top-P value. In such environments, the presence of variety is synonymous with failure, as you prioritize consistency and accuracy over any form of stylistic variance. When you shift your activity to tasks like creative writing or identifying novel perspectives, the objective changes significantly. Here, the risk is not that the model provides a standard answer, but that it becomes trapped in repetitive cliches that feel robotic to the reader. By increasing the temperature, you allow the model to traverse the probability landscape in ways that reveal unexpected semantic connections. This is how you simulate the difference between a technical manual and a thought-provoking essay within the same prompt structure. Recognizing that these controls are not merely dials but instruments for managing statistical entropy is key to becoming a proficient practitioner. You are effectively shifting between a rigid state machine and a probabilistic generator, depending on the requirements of the final output. If you cannot reach the desired model behavior through temperature alone, you can supplement these controls with direct instructions within your prompt. Telling a model to be precise, concise, or strictly logical serves as a linguistic directive that complements the underlying mathematical parameters. A prompt that instructs the model to act as a rigorous data auditor while having the temperature set near 0 creates a robust environment for verification tasks. In contrast, explicitly asking for multiple creative perspectives in a brainstorming prompt encourages the model to leverage the increased entropy provided by a higher temperature setting. Directives essentially communicate your intent regarding the search space to the model. While parameters control the raw physics, these text-based constraints guide the final output back toward the semantic goal. It is this combination of parameter-driven entropy and instruction-driven logic that allows for mastery over the output generation process. Focus on aligning your parameter choices with the explicit requirements of your prompt to ensure the model functions exactly as the task demands. See you in our next lecture. Welcome back to the course. In this lesson, we will explore the essential practices of prompt version control to maintain stability and reliability in your AI-driven workflows. Software development has long relied on version control systems like Git to manage the evolution of code, and we must apply that same rigor to our prompt engineering efforts. When you treat a prompt as a living artifact rather than a static piece of text, you acknowledge that your requirements change alongside the capability of the underlying large language models. Without a structured way to track these changes, you inevitably find yourself in a state of entropy where it becomes impossible to determine why a once reliable prompt suddenly produces degraded results. You should begin by establishing a central repository for your prompts, which could be as simple as a structured text file or a dedicated document management system. By recording the rationale behind every modification, you create a historical audit trail that serves as a diagnostic tool when model behavior shifts. This documentation should explicitly state the purpose of the adjustment, the expected output changes, and the specific model version used during testing. Such discipline prevents the common pitfall of losing an optimized workflow during iterative experimentation. Comparing the performance of different prompt versions requires a controlled and empirical approach to validation. You cannot rely on subjective intuition alone when assessing whether version 2 is objectively better than version 1 for your specific use case. Instead, you must curate a baseline dataset of inputs and corresponding ideal outputs that act as a regression sweep for your prompts. Whenever you modify an instruction set, you run your test inputs through both the legacy and the new version to evaluate consistency and quality. This comparative analysis helps you identify whether your modifications introduced unintended side effects, such as a loss of the tone you originally established or drift in the formatting logic. Even modest changes to a system instruction can produce nonlinear responses in complex models, so quantifying the delta in performance is essential. Maintaining a personal history of these trials allows you to revert to a known good state instantly if the new iteration fails to meet your quality standards. Sharing prompts within a team environment introduces complexity, as you must ensure that every collaborator understands the intent and structure of your instructions. In non-technical environments, you should adopt a standardized template that forces documenting the prompt's objective alongside the code itself. This documentation might include sections for the primary task, the target audience, example inputs, and expected output schemas. When teammates access these prompts, they should be able to read the metadata to verify if the prompt is suitable for their specific business logic without needing to reverse engineer the instructions. Standardizing the formatting ensures that even when someone else tunes the prompt, the changes remain readable and maintainable by the rest of the group. Think of this as a shared code base where contributors follow established conventions to avoid technical debt in their natural language instructions. Relying on shared naming conventions and clear descriptions prevents the fragmentation of institutional knowledge within your organization. See you in the next lecture. Welcome to the chapter on Advanced Technical Strategies, where we move beyond basic instruction to master directional stimulus prompting. We will explore how to steer model behavior using subtle linguistic nudges rather than brute force commands. Directional stimulus prompting is a technique that shifts the focus from explicit task descriptions toward the specific latent associations you want an AI to trigger. Instead of providing a full walkthrough of how a task should be completed, you provide a stimulus, a hint, a keyword, or a specific phrase that nudges the model toward a desired conceptual space. Consider the difference between asking a model to write code for a server and providing the stimulus. Use an asynchronous event loop architecture with non-blocking I/O patterns. The latter acts as a directional vector, constraining the solution space without requiring a verbose explanation of your architectural preferences. The primary goal here is to activate niche expert knowledge embedded within the model's weights that might remain dormant if the prompt is too generic. By strategically placing these keywords, you serve as a guide for the model's probabilistic engine, forcing it to traverse paths that are more aligned with your technical requirements. This approach is highly effective when you want to avoid contaminating the context window with long-winded instructions that the model might otherwise ignore or misinterpret. The psychology of model activation relies on the fact that LLMs are expansive associative machines designed to predict the next token based on a probability distribution trained on a massive corpus. When you provide a specific keyword, you're essentially increasing the probability of tokens related to that keyword's semantic context appearing earlier in the generation process. If you want a technical report that sounds like it was written by a senior systems engineer, you don't just ask for a professional tone. You insert stylistic stimuli like post-mortem documentation or infrastructure as code principles. These terms act as anchors, pulling the model's trajectory towards specific training data clusters that contain the linguistic markers of that expertise. Small instructional changes applied early in the prompt lead to large output shifts because these initial tokens define the hidden state of the generation. It is not about adding more information, but rather about choosing the high-leverage tokens that define the boundaries of the output you seek. One of the most common pitfalls when applying directional stimuli is the tendency to overwrite the model's internal reasoning with too many constraints, which negates the benefit of the nudge. You must practice the fine art of balancing subtle hints with direct instructions to achieve maximum impact without overloading the context window. Think of a direct instruction as the structural skeleton of your prompt, whereas the directional stimulus acts as the muscle that provides the desired tone and domain-specific depth. If the task is complex, start with a clear, concise instruction set, and then embed your directional cues near the start of the prompt to prime the model for the specific output style required. For instance, if you need a creative writing piece regarding distributed systems, you might instruct the model to explain database sharding while setting the stimulus to write in the tone of a hard-boiled noir novel. This separation of concerns allows the model to leverage its reasoning capabilities while staying firmly within the stylistic or domain boundaries you have established. As you begin to experiment with this, try to identify the specific keywords that act as gateways to the specialized knowledge you require for your daily tasks. If you are generating data, use schema-based stimuli. If you are generating prose, use thematic or stylistic stimuli that carry high semantic density. Avoid using vague adjectives that the model might interpret in unintended ways, as these create noise rather than direction. Remember that the efficacy of this technique is highly dependent on the model's base training. If you're prompting for obscure legal or technical concepts, you might need to use more specific terminology to ensure the model activates the correct associative cluster. This is an iterative process where you will eventually build a library of high-impact stimuli that work consistently across different, complex workflows. The beauty of this approach is that it makes your prompts cleaner, more efficient, and significantly more accurate by aligning the model's output with your intent through efficient guidance. I look forward to discussing the next advancement in our workflow during the next session. Welcome back. In this lesson, we explore how to move beyond simple output generation by implementing multi-step interactive audits that compel the model to verify its own work. When we ask an AI for complex information, it often prioritizes fluency over accuracy, leading to what we call hallucinations or logical lapses. By treating the generation process as a multi-stage workflow, we can disrupt this tendency through the use of self-critique. The strategy involves instructing the model to generate an initial draft and then immediately evaluate that draft against a predefined rubric or set of quality objectives. This technique effectively separates the creative phase from the analytical phase, even when both occur within the same generative session. The model must be explicitly prompted to act as both a creator and an editor, ensuring it views its own output with skepticism. Without this internal verification step, we are essentially accepting the first draft of an AI, which is rarely a sound engineering practice for technical or legal documentation. To implement this, You must structure your prompt to force the model into a recursive state of self-correction. Begin by providing your core task instructions, but append a secondary directive that requires the model to pause after generating the content. Instruct it to analyze its output specifically for adherence to strict constraints, factual consistency, and potential safety risks. You can force this behavior by asking the model to present the draft, followed by a separate block where it identifies its own weaknesses or ambiguities before producing a final, revised version. This creates a functional loop where the AI identifies errors in its own logic, errors the human observer might miss during a quick skim. You are essentially building a diagnostic layer into the prompt itself. This improves the qualitative output significantly because the model is forced to reread its contribution through the lens of a critic before committing it to the final response. In high-stakes environments such as legal review or technical compliance, such interactive audits are not optional, but essential for system reliability. You should define clear metrics for the internal audit, such as checking for the presence of specific legal clauses or confirming that all data points match the source material provided in the input. If the AI detects a mismatch, it must trigger a self-correction loop where it discards the erroneous portion and regenerates the content based on the identified flaw. This process should continue until the model confirms that all audit criteria have been successfully satisfied. By framing the prompt in this manner, you transition from simple input-output pairs to a more robust, state-based reasoning process. It is a form of design by contract for language models, where the output must satisfy specific conditions before the interaction can be considered complete. The beauty of this reflection pattern lies in its ability to highlight the limits of the model's current understanding. When the model performs this internal audit, it often uncovers subtle logical fallacies that stem from incomplete contextual data. By reviewing its own logic, the model frequently identifies areas where it lacks the necessary information to proceed confidently, thus preventing the generation of misleading content. Always ensure that the audit rubric is as precise as possible, as the quality of the critique is directly proportional to the clarity of the evaluation criteria you provide. This pattern is particularly useful for identifying hallucinations in technical summaries where numerical precision is required. By layering these critique steps, you create a system that is far more resilient to the common pitfalls inherent in large language models. Catch you in our next session. Welcome back. In this lecture, we shift our technical focus toward knowledge retrieval prompting, a specialized pattern for extracting and synthesizing insights from raw data sources. Knowledge retrieval prompting serves as the backbone for building reliable analytic pipelines where the AI acts as a sophisticated processor of provided information rather than a speculative generator. When we task a large language model with inspecting data, the primary design goal must be containment. The model should operate exclusively within the provided context window to prevent the inherent probabilistic nature of its training data from polluting the conclusions. We achieve this by establishing rigid constraints that force the model to acknowledge the source material as the single source of truth. If you fail to explicitly instruct the model that its output must rely solely on the provided text, it will frequently fill gaps using its latent knowledge, which leads to hallucinations. By defining your input boundary, using clear demarcations or header labels for the data being analyzed, you effectively shift the model's focus from creative association to extraction and synthesis. This transition from open-ended generation to grounded retrieval is what separates a professional tool from a casual chatbot experiment. Effective retrieval begins with the structural integrity of your input. You should always wrap large data sets in delimiters, such as triple backticks or custom XML-style tags, to distinguish the source corpus from your actual instructions. Within the prompt, you must define the precise nature of the synthesis you require, whether that involves gap analysis, contradiction detection, or multi-source comparison. When asking the model to compare two passages, guide it to categorize findings into specific buckets, such as shared facts, conflicting viewpoints, and missing information. For instance, you might instruct the model to identify any discrepancy between a statement in a technical document and an internal policy memo contained within the same prompt. By assigning specific roles to these inputs, you provide a clear roadmap for the model to follow during its logical traversal of the text. This systematic approach reduces the cognitive load on the attention mechanism, allowing it to preserve the subtle nuances that a looser, more conversational prompt would likely ignore. Beyond simple extraction, we can implement sophisticated search and summarization patterns that are particularly useful for business intelligence and academic research. When dealing with high-volume inputs, request that the model generate intermediate schemas or structured lists before it constructs the final summary. This prevents the model from rushing toward a summary, which often leads to the omission of minor but critical data points identified in the deeper layers of the provided documentation. Ask the model to perform a sanity check after its initial synthesis, effectively asking it to cross-reference its conclusion with the original source lines. This specific loop, process, verify, and document, ensures that the final output is both accurate and grounded in the specific data provided. If you identify a recurring pattern where the model seems to ignore specific sections of your text, verify the length of your input against the model's effective context window and consider breaking the analysis into smaller, discrete prompt iterations. Maintaining this level of operational discipline guarantees that your knowledge retrieval is consistent across varied documents and complex research datasets. See you in the next lecture. Welcome back to our journey through prompt engineering, where we now turn our attention toward the specialized domain of creative narrative architecture. We will explore how to steer large language models to construct complex stories while maintaining structural and thematic integrity. Building a functional narrative within an artificial intelligence system requires moving beyond simple content generation and toward a mindset of architectural design. When we speak of creative narrative architecture, we are effectively designing a roadmap for the model to follow so that it does not drift away from your established plot points or lose its grip on character voice. Consider the model as a highly capable but occasionally forgetful ghostwriter that needs constant access to a centralized record, which we often call a character Bible. By explicitly defining the thematic depth and the target pacing before asking for a single sentence of prose, you create a scaffolding that prevents the collapse of long-form work. This is the difference between a prompt that produces a fleeting anecdote and a system that maintains a consistent thread over several thousand words of output. If you fail to impose these constraints early, the model will invariably succumb to its inherent tendency to optimize for the most probable next word rather than the most narratively significant one. Maintaining character consistency across a long-form creative project represents a significant challenge because the model's context window does not naturally prioritize character history unless you force it to. The most reliable method to solve this is to treat the prompt not as a request, but as an ongoing maintenance task where you update a structural summary as the story progresses. Every interaction should begin by anchoring the model in the current state of the story arc, reinforcing the specific traits and motivations you have defined in your initial configuration. You should approach your prompt design by treating the prompt as a configuration file for a piece of software, where variables such as tone, dialect, and internal contradictions are strictly delimited. When you allow the model to deviate, you lose the thematic density that defines high-quality creative work, resulting in prose that feels generic or disjointed. By maintaining a modular structure in your input, you allow the model to parse the narrative architecture without blurring the lines between disparate story elements. Controlling the pacing and metaphor density requires a deliberate intervention in how the model parses your stylistic directives. If you simply ask for a story, you will likely receive a flat narrative that progresses at a medium pace without any meaningful variation in sensory description. To counteract this, You must explicitly encode pacing instructions directly into the prompt using temporal markers or structural constraints that dictate how much time passes between key events. Metaphor density follows a similar logic. You can instruct the model to increase its use of figurative language in scenes of emotional high stakes while demanding a sparse, direct style during informational bridge sections. This separation between the atmospheric goal and the granular action allows the model to shift its stylistic output without losing the logical thread of the plot. You are effectively acting as a director on a film set, providing high-level directives while letting the under-the-hood engine handle the mechanics of descriptive composition. Collaborative storytelling is essentially a negotiation between human intent and machine probabilistic generation of language. You must assume the role of the primary architect, holding the vision of the plot points while delegating the repetitive, granular prose generation to the model. This workflow is successful only when the human provides constant, incremental feedback that corrects deviations from the narrative plan before they propagate into the rest of the text. By dividing the work into distinct segments, you ensure that the context window remains focused on the immediate narrative requirements rather than being forced to juggle the entire architecture at once. Think of this process as a pipeline where each iteration refines the previous output based on your oversight, creating a system that improves as the story unfolds. If you treat the model as a partner in this process, you gain the ability to scale your creative output in ways that traditional, manual writing simply cannot support, provided your foundational directives remain clear and unchallenged. See you in the next lesson. Welcome back. In this session, we will explore how to transition from basic prompting to leveraging large language models for professional-grade data interpretation and analysis. When we treat an LLM as a non-coder data analyst, we shift our focus from simple text generation to objective pattern recognition. Much like applying a rigid interface in object-oriented programming, we must establish clear boundaries for how the model perceives raw input. You should always begin by providing a clear definition of the persona the model is expected to adopt, such as a senior data analyst specializing in qualitative research. Without this explicit role assignment, the inherent probabilistic nature of the model tends to drift toward anecdotal commentary rather than structured analytical output. By enforcing this persona, we align the internal weights of the model with the statistical expectations of professional data processing. This is particularly effective when dealing with large volumes of unstructured textual data, such as customer feedback logs or raw market research transcripts. Effective thematic coding requires us to define a taxonomy of categories before asking the model to perform the classification. You cannot expect consistent results if you ask the model to analyze a dataset without providing the specific thematic buckets in which you want the data partitioned. If you provide a list of categories along with brief semantic descriptions for each, you significantly reduce the likelihood of the model hallucinating irrelevant labels. This process resembles the way a developer writes unit tests to verify that a specific input always returns the expected output state. When you request sentiment analysis, ask the model to provide a confidence score alongside its assessment, which forces it to demonstrate its reasoning process. This requirement acts as a constraint that prevents superficial analysis and encourages the model to look deeper into the linguistic nuances of your provided text. When handling tabular information, we must treat the model as a data processor that requires a clean input stream. Markdown tables are the preferred medium for this interaction because they provide a structural hierarchy that the model can easily parse without additional transformation layers. If your data is in a comma-separated format, ensure that you explicitly mention the column headers in your prompt to maintain semantic integrity throughout the analysis. When analyzing outliers, instruct the model to use specific statistical criteria, such as identifying items that deviate beyond 2 standard deviations from a mean in a provided numerical distribution. Simply asking the model to find what is unusual often leads to generic observations that lack professional utility. By grounding the search for outliers in defined criteria, you transform the LLM into a reliable tool for identifying anomalies in internal business documentation. Converting qualitative feedback into actionable business intelligence requires you to implement a rigid inquiry framework within your prompt. You should instruct the model to ignore surface-level noise and instead focus on recurring friction points that align with specific business goals. For instance, if you are analyzing market reports, explicitly request that the model maps identified trends to your current organizational pillars or product strategies. This limits the scope of the intelligence generated, ensuring that the model provides a synthesis that fits correctly within your existing institutional context. You are essentially creating a pipeline where raw textual data flows through an analytical filter defined by your operational requirements. This approach removes the need for custom Python scripts, as you're providing the logical structure that would otherwise be handled by procedural programming. Trend prediction relies entirely on the model's ability to maintain context over the sequential nature of your historical data. When you present historical data sets to the model, always include a date or version indicator to ensure that it respects the chronological order of the entries. Without these markers, the model may incorrectly interpret seasonal or periodic variations as isolated events. If you ask for a trend forecast, force the model to provide a rationale for each prediction based on the specific evidence found in the data you supplied earlier in the prompt. This forces a connection between the output and the input, effectively grounding the model's conclusions in the reality of your dataset. Such discipline prevents the model from generating overly optimistic or disconnected forecasts that could mislead your strategic planning. As you build these analytical prompts, remember that the quality of your output is directly proportional to the constraints you apply to the model's behavior. A prompt lacking specific instructions on what to ignore is as dangerous as a function that fails to validate its inputs. By defining your taxonomy, setting structural requirements for tables, and enforcing a specific inquiry framework, you ensure the model behaves like a consistent analytical service. You may find that adding a few examples of desired output, fewer in contrast to the rigid coding examples, since this is qualitative, helps the model understand the tone and granularity you expect. This deliberate approach to prompting ensures that your data analysis remains objective, reproducible, and deeply aligned with your actual business needs. I will see you in our next session. Welcome back. In this chapter, we will explore the nuances of synthesizing complex perspectives to move beyond linear thinking when interacting with large language models. To effectively synthesize complex perspectives, you must first understand that a model's output is a reflection of the constraints you impose upon its reasoning process. Instead of asking for a single answer to a multifaceted problem, you should construct prompts that force the machine to inhabit multiple, often contradictory, roles simultaneously. Think of this as creating a virtual committee or a debate chamber where the quality of the resolution improves through the friction of competing ideas. By assigning specific expertise and distinct worldviews to different personas, you prevent the model from defaulting to its most common or generic training data distributions. This deliberate imposition of structural conflict compels the system to engage in a more rigorous internal validation, as each persona must account for the rebuttals of the other. The goal here is not to elicit a consensus immediately, but to map out the entire problem space by highlighting the logical trade-offs inherent in any strategic decision. When we use role-based prompting to simulate cross-functional discussions, the precision comes from the specificity of the constraints assigned to each role. You cannot simply instruct an AI to be a manager or an engineer. You must provide a narrow, context-aware profile that includes specific goals, potential biases, and a distinct vocabulary for that persona. For instance, if you are analyzing a market expansion strategy, you might prompt the AI to define the operational risks as a cynical risk manager, while simultaneously generating growth projections as an optimistic venture capitalist. By demanding an iterative debate where these personas react to each other's points, you expose blind spots that a single perspective query would almost certainly miss. The prompt should explicitly require the AI to maintain these personas across exchanges to build a cohesive narrative of conflict. This simulated struggle is exactly what reveals the hidden variables, such as resource constraints or market saturation, that usually remain buried in standard, one-dimensional outputs. Once you have generated these diverse outputs, the final step is to synthesize them into a comprehensive decision matrix that prioritizes objectivity. A common failure mode in this process is allowing the model to simply summarize these views in a way that prioritizes the most pleasing or coherent argument over the most accurate one. To combat this, you must instruct the model to act as an impartial adjudicator whose sole task is to score each viewpoint against a defined set of criteria, such as economic feasibility, technical debt, and long-term sustainability. By forcing the AI to build a table or a weighted matrix, you introduce a mechanical structure that filters out the emotive language typically found in simulated debates. This forces the model to justify its synthetic final recommendation by linking it directly to the evidence presented by the earlier personas. In effect, you're using the logic built into the role-based phase to inform the quantitative rigor of the decision matrix. Addressing bias during this synthesis phase is perhaps the most difficult aspect of advanced prompting because large language models are inherently trained to seek agreement. To ensure a balanced analytical approach, you must inject prompts that explicitly challenge the model to identify its own underlying assumptions in every step of the synthesis. Use techniques like the debate pattern to stress test your ideas by asking the model to adopt a contrarian perspective specifically to find flaws in the current logic. If you're developing a strategic plan, ask the system to act as a red team analyst whose success condition is explicitly tied to finding at least 3 fundamental weaknesses in the previous synthesis. This prevents the model from settling for a comfortable middle ground, which is often the most dangerous outcome in strategic planning. By institutionalizing skepticism within the prompt workflow, you force a more nuanced evaluation that is significantly more robust than a default generative response. See you in the next lecture. Welcome to the final chapter, where we will consolidate our understanding of the core prompting pillars and establish a sustainable strategy for continuous growth in this field. We will synthesize everything we have learned to ensure your future engagements with AI models remain high quality and reliable. Reflecting on our journey, we have explored the essential pillars of effective prompting: role, context, instruction, and output. When you assign a clear persona to the model, you narrow the latent space of potential responses, significantly increasing the relevance of the output. Contextual grounding acts as the anchor, providing the necessary boundaries and background information that prevent the model from drifting into hallucinated or generic territory. By combining this with explicit, actionable instructions, you transform a general-purpose processor into a specialized tool tailored for your specific domain. Finally, defining the expected output format, be it JSON, a structured table, or plain prose, ensures that the information received is immediately useful for your downstream workflows. Mastery is not about memorizing complex tricks, but about consistently applying these fundamental constraints to every interaction. To elevate your performance, we must revisit the most effective prompting techniques, such as chain of thought and few-shot prompting, which serve as the backbone for complex reasoning tasks. Chain of thought is particularly powerful when you require the model to explain its logical steps before providing a conclusion, as this transparent reasoning process reduces internal consistency errors. Conversely, few-shot prompting bypasses the need for intensive training by providing the model with a few high-quality examples of what success looks like. These examples act as a template, guiding the model's pattern matching capabilities toward the desired structure and tone. When you combine these, you effectively simulate the cognitive architecture required for advanced problem solving. Developing an intuition for when to deploy these techniques is a mark of a practitioner who understands the underlying mechanics of large language models. As you continue to evolve your skills, it is essential to cultivate a personal prompt portfolio that serves as a living, documented history of your successes and failures. Treat your prompts as code, keeping track of different versions and the specific logic that led to the best results for recurring tasks. This repository becomes an invaluable asset as models are updated by their providers, allowing you to quickly benchmark new versions against your established high-performance prompts. You must also remain mindful of the ethical implications of your AI practice, ensuring that your usage remains aligned with privacy standards and bias mitigation strategies. Effective prompting is not a one-time event. It is a collaborative loop where your communication skill directly limits or expands the capabilities of the agent you're guiding. The landscape of generative AI changes rapidly, yet these core principles of logical structure and clear communication remain the most reliable way to stay ahead. Building a thriving learning practice in this field requires you to adopt a habit of continuous, critical evaluation of the model's outputs. You should treat every result from the model not as a final answer, but as a data point that confirms or falsifies the assumptions you embedded within the prompt. Whenever you encounter a failure, perform a rigorous post-mortem analysis to identify which of the four pillars, role, context, instruction, or output, caused the discrepancy. If the output format was incorrect, examine the rigidity of your constraints. If the tone was wrong, revisit the role definition. This methodical approach ensures that you are constantly refining your mental model of how different architectures process information. By documenting these insights, you transition from someone who simply uses a tool to someone who understands how to engineer reliable systems in an inherently non-deterministic environment. The future of human-AI collaboration relies heavily on our ability to translate complex human intent into structured instructions for intelligent systems. We are moving toward a world where the ability to guide an AI effectively will be a primary competency for almost every professional discipline. As the models become more capable, the role of the prompter shifts from providing surface-level commands to designing architecture, logic, and long-term strategy for automated tasks. Keeping pace with these updates requires a balanced approach of staying technically informed about new features while remaining grounded in the timeless logic of clear, unambiguous communication. You have developed the necessary skills to navigate this future, provided you continue to treat prompting as a precise, iterative discipline rather than a superficial interaction. Your commitment to these fundamentals will ensure that your work remains relevant even as the underlying technologies perform increasingly complex tasks. I look forward to seeing your progress as you apply these final strategies to your professional projects. Good luck on your path to mastery.